Hello and welcome to Stats. Our next set of notes, we are covering section 5.2, binomial distributions. This is going to kind of come into connect to what we saw last section with the probability distribution, so there'll be some similarities, some new things we'll use on the calculator though, a little bit of differences. This is our last set of notes before the first exam, so you should be getting ready for that first exam, making sure you've completed all the homework and quizzes, doing some reviews. You should be able to find those in detail in my lab. So get ready, make sure that you're prepping for that exam. You want to make sure you know what you're getting into. So make sure you're going over your material and getting ready for that. It's coming up soon. Okay, so let's talk about binomial distributions. So we talked about probability distributions in the last set of notes. And these probability distributions were showing all the different possible results for a random variable and then percentages or probabilities for each result. And they kind of made a chart out of that, and charts could be big or small depending on how the different results are. Well, a binomial probability distribution is a specific type. It's probability distribution where we deal with situations where the outcomes only fall into two categories. There's not more than two categories. There's only two options. Examples would be like heads or tails, there's only two options. Cured or uncured, passed or failed. These are all situations that deal with just two different options, yay or nay, yes or no, success or failure. There's a lot of situations in life that can be boiled down to this type of situation. Because it's a little simplified, there's some handy math for it for figuring out some different values. So we're going to talk about what to do with this. So again, binomial probability distribution is a probability distribution with outcomes falling into only two categories. That's what makes it binomial, bi meaning two categories. Now to be a binomial distribution, of course, you have to meet some requirements, some criteria. First thing is you do have to have a fixed number of trials. So you can't have a thing that just goes on and on and on. This is something where there is a certain number of things being tested overall. So fixed number of trials, this is going to be like your population that you're studying kind of idea. Each trial is going to be a single observation. So each survey you hand out, each person that receives the new test drug, each one of those people, each time you flip your coin, that would be a trial. And there should be a limited number of these. They should be, they go so far and then they stop. Next thing, the trials need to be independent. So remember when we flip our coin each time, the probability doesn't change over time. That's independent. So the trials do need to be independent. The probability, what happens with one trial doesn't affect the next one. If this person gets cured from the drug, it's not going to affect whether or not the other person is cured by the drug, which is why a lot of drug studies won't let people that are from the same household, same family, stuff like that, both be in the drug trial, because then they might have some influence over each other. So they're going to find random patients with no obvious connections, and then they'll test those people, at random instead of people that are obviously connected. So trials are independent. They do not affect each other. So the outcome of one does not affect the outcome of the rest. Next thing, each trial must have all outcomes in one of two categories. As we said earlier, it has to be only two options. You can't have more than two options. So outcomes fall into just two categories. The typical way of labeling these are success and failure, but don't let that mislead you, because you see success and failure, you think, oh, there's the good option and the bad option. Well, the success option is just what you're looking for. So success could be, yeah, I'm testing a new drug, and the success is that it saves the patient. Or if I'm doing a study to see if this has a negative side effect, maybe it makes you go blind. Success might be you went blind. I know that sounds terrible, but that's what you're looking for, because your study is trying to figure out, how many people from this, drug got the side effect. So success would be someone that got the side effect of being blind. So success and failure aren't always good and bad in that sense. One of these might be good, one of them might be bad, but it might be backwards, or they might just be two different options. But they're the only two options. You either had the side effect or you didn't. You went blind or you didn't. That would be the only two options. So that's what makes it important, is there's only two different results. Then the last thing is the probability of success is the same for all trials. So one person's not going to have better probability than the next. There's no reason to assume that like this group is going to have higher probability of the thing happening than this other group. So probability is the same for all trials. Okay, so you should be able to determine by reading about a study or some kind of situation whether it fits into being a binomial probability distribution. If it meets those requirements. So these binomial probability distributions have to meet these criteria or requirements. So let's look at a couple examples and decide if we can figure out if they meet the requirements. So first off, we are testing graduation rates. A high school principal checks a list of students that started high school 4 years ago against the current list of graduated students. So first off, does the procedure have a fixed number of trials? Well, yeah, there's only so many students that came in, right? So there's a limit to how many students that were on that initial list. So there's only so many trials. So yes, list of students is number of trials. So far it's good. Is a fixed number of trials. Next thing, are the trials independent? In this case, we'd say yeah, because this student A graduating doesn't decide whether or not student B is going to graduate. In real life, you could maybe argue it's a little more complicated than that, but we'll try and keep it simple and just say, these are random couple students at the school. They're not going to really affect each other who graduated. So we'll say yes, it's independent. Especially if you're looking at like a huge high school and you only look at a few students out of that, they might not really have any connections, kind of thing. Trials must have outcomes in only two categories. Two categories in this case would be graduating or they're not graduating. So yes, we have two categories. We have graduating or not graduating. In this case, we would call graduating success because he's looking to see if they're graduating. What's the success rate on those? So that one, yeah, that meets. Last thing, probably has to be the same for all trials. And in a case like this, we'd say, yeah, we're probably going to use a general rule of thumb. And he's probably looked up statistics in the past and said, 75% of students graduate, and so then he'll just use that as his probability. He's not going to build this on different students. Now, if you're doing this trial and you did break it up into maybe ethnic groups or social classes or something like that, then you might say the different classes or ethnic groups might have different probabilities of graduating, and in that case you have to do it differently. But if we keep it simple and we just say overall the whole class has a certain rate of graduation, and that's what we're going to use as probability of success, the probability of graduation for each student, then we'd say yeah. So this one, it meets all three. So yes, it meets all three, or all four, sorry, it meets all four criteria. All have the same chances. So yeah, it meets all those things we're looking for. So we can say, yep, that is a good binomial. There's only two options. Probability distribution where we have, fixed number of trials. There's only so many of them. Each one's independent. They're not affect each other. Everybody's got the same chances. That's what we're looking for. Let's try with playing cards. So playing cards, the dealer gives out cards one at a time from a standard deck. Player wins the pot if they receive a face card. You can see some things go well, like wins the pot if they receive a face card. So there's win or not win, right? You get the pot or you don't get the pot. So there's only two options. Fixed number of trials, there's only so many cards in the deck, so this is fixed number. But this one does not work because as he deals out the cards, the chances are changing, right? Each time he deals out a card, going one at a time, he's not taking the cards back. If there's no replacement, which it doesn't say anything about replacing the cards, so we're going to assume there's no replacement, then it's not independent, because every time you give someone a card, the next card, well, now there's less cards in the deck, there's different cards in the deck because you took one out, so then that probability is changing for the next person. So each trial is not going to be have the same, they're the same as based on what previously happened. They're all going to be having different chances as the cards change. So this is definitely a no for this one. Okay, making decisions. George and Pete use rock, paper, scissors to decide who will choose the next activity. Choice of George if he wins. So this one actually can kind of break it, and you can kind of go yes or no. Depends on how you deal with it. You might say no if you think of three outcomes, because you could say the outcomes are, George wins, George loses, but there's also, of course, rock, paper, scissors. You could have that he ties. So if you have three different options, then you'd say no. That's not binomial because binomial can only have two options. But you could say, or yes, if you turn it into a different situation where you say, okay, that either George wins or George doesn't win. Now there's only two outcomes, right? There's the outcome he wins or the outcome he doesn't win. And in this case, you'd say, yeah, that now there's only two outcomes. Probability Success is always the same, right? When you play rock, paper, scissors, whatever you choose, there's always the same chances that one's a winning throw. It's independent, so the previous throw doesn't mean, the game, round of rock, paper, scissors doesn't mean the next one's going to change. You still have the same chances of winning every time. And we could just say a limited number of trials, he's only going to do it so many times. So yeah, it actually could work as long as you categorize it right. So you'd have to make sure you break this down into just George wins, George doesn't win. As soon as you make 3 categories, then you'd say no, it doesn't work. So you kind of have to be careful about how you pick your categories. And that's if you're a statistician running a survey or a study, if you can design it so there's only 2 possible outcomes, then you can avoid that kind of, I can't use binomial distributions. But if you design it with two possible outcomes, then you can. So that's something someone's going for. They're going to make sure they can try to meet all 4 of these requirements. Because if you meet those, then you'll have a nice binomial probability distribution. Again, this is going to be a simpler, easier method thing, and we'll see there's actually some nice calculator techniques for doing this. So that's what we're going to be working with. In this section, we're going to be working with binomial probability distributions. And what we're going to do is we're going to be finding probabilities. Now, one thing that happens in real life is a lot of times we'll actually be choosing samples without replacement. Because when you go and do a survey or do a study with people, you don't pick the same person over and over again. I'm not going to hand out a survey to a person and then go find the same person and hand them another survey. I'm going to pick a group of random people, and they're all going to be different people, and they're all going to get one survey. Now, we did mention previously, when we were in the probability section, that it's okay to do this where you're picking people without replacement as long as your sample is small enough and your population is big enough. We said, hey, if you have a really big group of people, you choose a small sample, then you weren't going to pick the same person anyways, so it's okay, and you can treat it like it's independent. And that's what this rule is right here. This is telling us the actual numbers for the rule. So the rule says if your sample size is no more than 5%, so if you don't pick more than 5% of the population, then you can treat it as independent. So if it's no more than 5% of the population, then even if there's no replacement, so without replacement, it can be treated as independent. So that's the big thing here. So typically, yeah, we're not going to pick the same person. So technically, we're doing dependent because we're not picking the same person over and over again. We're saying, oh, we took them out of the runnings. Now we have a different group left over. But if we pick a small group out of a big population, it's okay. So small sample from a big population, then we can treat it as independent. So that's something we'll always have to worry about. If you go out and do a survey or whatever, if you take too big of a sample group from too small of a population, if I look at the 20 kids in my classroom and I take 10 of them for my sample, well, it's too big now. I've picked too many people. Now, if I only pick 2 students from that class, then I'm probably okay because I'm down to like 5%. But that's not a very big sample. So I'll probably usually try to work with a bigger population. Instead of just working with one class, I might work with all my classes. And then I've got a couple hundred, so I can take actually a little bit bigger sample than just 2 students. So a small sample from a big population, that lets us do the math of being independent. That's something we always have to be careful with when we're doing statistics. Okay, so what we're going to do, we're going to find probabilities of certain results. So you're going to do these binomial probability distributions, and you're going to think, okay, I'm picking out of a group, maybe there's 100 people I'm picking out of. I'm going to look at, say, the probability of success, whatever success is. Maybe it's like 60%, 70%, whatever. And then I'm going to try and figure out what the probability is of getting so many successes out of my sample. And so, like, if you're doing a drug test, what you might be doing is just thinking, I want to look at the likelihood my drug will cure people. So I'm going to think, okay, I have a drug study, I have 100 people in my study. I think that with one person, I've done some research, I think that the probability of the success of this person curing is 80%. Most of the time it works. And then what's the probability that out of my sample of 15 people out of those 100, that 10 of them get cured? And I can look at those probabilities. What's the likelihood? And we can compare those probabilities. So that's what this idea is for. Binomial probabilities, we're finding the likelihood of things happening. And this is what people use when they go on to do these real statistical studies is, what are the probabilities that people get healed based on the information I have? Okay, so to do this, you need to be able to define some values that are going to be really important. First thing, you're going to look at X as being the number of successes. So when you do your study, how many people got the success? Again, this could be good. It could be the, hey, this cured my disease, this drug was great, or it could be bad because it could be the, I'm that person who got the side effect. So success, again, is just what we're looking for. Did you get the side effect? Did you get cured? Did you graduate? The success. Next thing is N is the number of trials. So how many people were participating in this study? So how many people did we give the drug to? How many people were in that class list? We're looking to see, how many people graduated. So N is the number of trials. It's your sample. It's your group that you're studying, kind of thing. When the probability of success is P. So P is the probability of success. So this is the likelihood that the drug cures the person, the likelihood the person graduates. So when I said, 70% chance they graduate, or 75% chance they graduate, that was P. When I say the drug cures 80% of people, that's P. The probability of success. We'll use Q for the probability of failure, which, because these two are mutually exclusive, either you succeed or fail, those are the only two options, you can always find Q by just doing 1 minus P. Remember, if there's 80% chance of success, well, then what's the chance of failure? Well, that's 20%, right? Because 1 minus 0.8, or 80%, 1 minus 0.8 is going to be 0.2, or 20%. So that's what you can use for Q. It's always going to be some probability of failure. Okay, and this is the formula. So this is our formula for finding the probability. If you have X successes, N trials, P is your probability of success, and Q, or 1 minus P, is your probability of failure. And that's our formula right here. So we'll do this with this problem down here so you can see how it works. So first off, we have 60% success rate. So you can see how that would be P, because it's probability of success. We have 10 patients that are treated. So that's going to be our number of trials, right? We had 10 trials because we had 10 people that got the drug. And 3 of them, exactly 3, are going to be cured. Well, that's the number of successes. So that's going to be X, or number of successes. What would Q be in this case? What's Q? Well, remember that if P is 60%, we just take 1 minus 0.6 gives us 0.4, and that's Q. So again, 1 minus P equals Q. So you can always find the Q. If you know the probability of success, you can always find the probability of failure. So failure, Q would be 40%. Okay, so let's throw these in this formula and get an answer for this. So I'll get our probability. So probability of X successes, where we're looking for 3 successes. Probably getting 3 successes, replacing X, we're saying 3 is how many we want. We're going to have N trials, so N is the number of trials, that's 10 patients. So 10 factorial goes on top. On the bottom, we actually do N minus X. So we're going to take the 10 patients minus the 3 successes, subtract that at the bottom, and that also gets a factorial. And then X, again, is our 3 successes, so we'll put 3 factorial in there on the bottom. That's the first part. Then you have P to the X. Remember, P is your probability of success. Make sure you do this as a decimal though, so I want 0.6 to the third. And then Q, again, is the probability of failure, so I'm going to take my 0.4 for Q, 0.4, and this goes to the N minus X power, so I'm going to do 10 minus 3 power. Okay, so I'm just going to go ahead and type that in the calculator, and that'll tell us the probability that 3 of those 10 patients are cured. We can just type that in the calculator and find that out. I'm going to type in, to get this type in, I'm going to type 10, hit the math button, remember, because that's where you go to probability, and the factorial is option number 4, so probability 4. Type that in, divided by parentheses. I'm going to put parentheses, I'm actually going to put 2 of them here, to make sure this goes in right. 10 minus 3, close that first parentheses, and do a factorial, so math, probability, factorial, times this other 3 factorial, so we're going to 3, and then do another math, probability, factorial, and then I'm going to close the parentheses, because I wanted the parentheses on the bottom, because there's always implied parentheses when you do fractions like this in your calculator. So I got that closed off. Now I'm going to do times 0.6, because it's 0.6 to the third power, so 0.6 to the third. Make sure if you have a calculator like mine, you get out of the power before you type the next part, so I can do times 0.4 to the, and I'm going to do parentheses around this power, 10 minus 3. Okay. All that in there should give me an answer. It looks, yeah, that looks like what it's supposed to be. It gives me 0.042467. And this is a decimal, so if you turn it into a percent, it's going to be 4.2467, or you could round it to like 4.25. Again, my math I will tell you what to round to, but that's the percent. Remember, you always get this percent by just moving the decimal 2 spots. And that's how you get the percent. So if someone asks, what's the probability that 3 of these 10 patients are cured, exactly 3 of them are cured, you'd say it's 4.25%. That's the probability to get cured. Now, the formula is pretty cool and it's useful, but it'd be nice if we didn't have to type all this in our calculator and do all that. And then actually, you don't have to do that. Because if you have the nice T84 plus, it'll actually do this calculation without you having to use the formula. You just have to tell it what the probability of success, the number of patients, and the number of successes are. If you give it that information, it'll work. So let's do that. We're going to use the calculator to find these probabilities for binomials. So to do this, we just need to find how many successes there are. So if I'm doing exactly X successes with N trials and a success rate of P, so again, P is your probability of success, then you use this set of steps. So first you're going to go to second button so that you can use the distribution. So if you go to the second button and hit distribution, it's this little DISTR right there. It says bars on the actual button, but DISTR is above it. And then you want to scroll to the bottom. Now, there's 2 ways to get to the bottom. One is to sit there and hold down for a long time because this is a fairly long list, and you get there. Or the other way is you can actually jump up from the top. You can actually jump to the bottom. So if you want to jump to the bottom, just go up one, and it jumps all the way to the bottom. And then you can see the binomial PDF is pretty close. So that's what we're going to use. We're going to use binomial PDF. Binomial PDF is the one we want when we're doing exact. They say you want this many exactly. Like last time we wanted exactly 3 people cured. And so you do binomial PDF and hit enter. If, however, you don't want exactly that many, most of the time we don't want to know exactly 3 people got cured. We want to know at least 3 people got cured. So a lot of times we'll be doing 3 or less. And in that case, we'll do CDF. That's why there's 2 options. There's PDF for exactly, so when you want exactly that many. CDF is for that much or less. And that's why that makes a difference. We'll actually use CDF more often than use PDF. But either one you use, whichever one you're using, after you do that, your next step is to, after you hit enter on the PDF, is to type in your value. So if I just go back to the last one where we said that N was 10, because there were 10 trials, I just put in 10, and then press enter. And then I type my P, which is, we said the last one was 0.6 for 60%, and we type in enter. And then we hit the X value, how many successes? Well, we said 3, and hit enter. And then I hit enter again, and then hit enter again. That's why it says hit enter 3 times. Then it'll give you the result. So there it is. Now, my calculator is a little fancy. So you saw how it did that when we did the second distribution and did the binomial PDF. It gave you like the places to put those in, the trials, the P, the X values. I did all those, and then I hit enter, and then it typed it out, and then I hit enter and got the result. And it's the same 0.0424. It's the same result we got before. Your calculator might not do it quite the same way. So you might not be able to actually sit there and type in like the 3 different values with enter, because it might just put binomial PDF on your calculator screen. And then, so like it'll look like this, where you just, you hit binomial PDF, it might just look like that. And then you'll actually have to just type these with commas. So you'd have to like type 10, comma, 0.6 for the probability, 0.6, comma, and the 3. And you might just have to type it like that, where you actually had to type each value with commas in between. It'll look the same as what I got, but it doesn't just write it out for you. But you always want to put the N value first, the P value second, the X value third. So again, when you're doing this, when you're doing a binomial PDF, it's going to be N at a P, X. So P and X. And you put commas between. So if your calculator doesn't do it like mine, where it's fancy, because I got the fancy color, super special calculator, if it just gives you a binomial PDF, you have to fill it in. Just type N, P, and X with commas between. And again, always use decimal for P, and you should be good. But that's one way to get. That's the way to get this probability without actually using the formula. So you really don't need this formula. We don't need it if you use the calculator. You'll see that a lot with this class. There's lots of things where if you use the calculator, then you can kind of get away from the formulas a little bit because the calculator has those built in already. and saves your life a little bit with having to do all this. Okay, so let's look at an example. The hardest part now, because we have a calculator will do it for us, is really just determining what the NP and the X are. So we'll read a problem and figure out what those are. So use the calculator to find the probability of the following. A certain high school has determined the chances of a student graduating are 60%. So we see that the 60% is the chances of graduating. The principal is curious about a grade with 186 students. What's the probability that 100 students will graduate? So if I look at this, I realize that the first number they gave us, 60%, is going to be our P. That's our probability. So P is 0.6, right? 60% turns into 0.6 or 0.60. The 186 is going to be the N, right? So N is going to be 186. And then this 100 students, that's exactly how many we want to figure are going to graduate. That's going to be our X. Now, I didn't write these down in order, so again, when you do this, make sure you do them in order. So you have the binomial PDF. You always want to start with the N first, so 186 would go first. The P, which would be 0.60, 0.6, and the X, which is 100. So that's how you type it in. Again, if your calculator is not helpful, that's how you have to do it. If you got a calculator like mine, it's not so bad because you just let the calculator tell you what to put in. So I go to Binomial PDF, tells me to do the number of trials, which is 186, because that's how many students were there in the school. To do the N or the P value, which is 0.6, that's the probability, and the X value, which is 100. So I'm looking for exactly 100 students graduating. Type it in, hit enter a few times, and I see that the probability answer is 0.01326, and I'm just going pretty far because I want to turn this into a percent, so this ends up being 1.326%, or 1.33 if you wanted to round it. So that's percent. That's probability of exactly 100 graduates. What if instead you want to do something like 110 or less? Well, I'm not going to sit there and do 110, 109, 109, 108, 107, and do all the way down to 1, because that'd be silly. That'd take a lot of time. So instead, we just use the CDF option. So when we want to do 110 or less, well, that just means that now our X is going to be 110. We're still using the same N as 186, and the same P as 0.6. None of that changed, but we're just looking for 110 or less. So we're going to do that binomial CDF because it's built to do that much or less instead of just that much exactly. And we'll put in the same values, 186 for the trials, the 0.6 for the probability, but we'll change this to 110 because that's that much or less. We're looking at 110 or less. So again, I'll hit second distribution, go to the CDF option. So again, CDF is that much or less. This might be something you want to put on your note card to remember. The PDF is exact, CDF is less than or equal to. Trials, we said we're going to do 186 students in the class still. 0.6 is still our probability, but now our X value is actually 110 because we said 110 or less. Put that all in, so it should look just like what I have right here, but only CDF and all those numbers. And we get a value. And you'll notice this value is going to be a lot higher because this one's 0.4327, which turns into a percent. It turns into 43.27%. 43% is way higher than 1%. Because again, this is not just exactly 100 people get cured. This is 1 person, 2 person, 3 person, 4 person, 5 person, all the way up to 110. This is all those options. So, if you did the same thing with 100 instead of 110, it's still going to be way bigger than the first one because the first one is exactly just the case where exactly 100 people graduate. The next one is that much or less. So there's a lot more options because the first one doesn't care if 99 people graduate. It only wants exactly 100. This one, yeah, includes 99, includes 98, 97, 96, 95, all those ones. Everything from 110 all the way down to 0 people graduate. All those options are included. That's why this one's such a bigger percentage. And typically that's what we care about, right? The teacher's the principal's want to know what's the probability that he has this much or fewer, because anything less is more extreme is not going to be something he's going to toss out. He's going to look at that as a result too that he cares about. So that's the idea. Okay, so we're going to do a couple more using the formula, get some practice, but that's really most of this section. We got one page at the end that's a little different, but a couple of the next ones are just more practice. So in most cases, again, we're not going to look at probably the exact number. That's just not very common. So again, this would be our PDF exact number, which is the PDF. We're not going to do that very often. In most cases, we're not going to do that. Instead, we're going to be looking at probability of a minimum or a maximum. So we're going to be typically working with the CDF to do minimum or maximum CDF. Now, you'll notice the CDF only did that much or less, so we'll have to talk about how you do more. We'll talk about that as we go through here. So we're usually going to be doing with at least or at most is kind of what we're going to be looking at. Okay, so use the procedure to find the probability of the following. A certain high school has determined the chance of the student graduating is 70%. So 70% now is their chances of graduating. That would be your P, right? P is always the chances of success. We'll say graduating is probably success in this case. The principal is curious about a group of 5 students. A group of 5 students, not a very big group, so there's not very many trials. So this would be N, would be number of trials. First case, he's looking at most 2. So what's our X in this case? Well, at most 2 means 2 or less, right? 1 counts as a most 2, it's not bigger than 2. 0 counts, 2 counts. This is 0, 1, or 2. So this is 2 or less. That's what we're looking at now. So since it's an or less one, since this is this much or less, this is a binomial CDF. Again, CDF because we're looking at that much or less. Since we're looking at 2 or less, at most 2 or less, that's where we're going to do CDF. When we do CDF again, we put in the first number is N. So we said N was our 5 students, so we put 5 in first. Second number is P. In this case, it was 0.7, so we put in our 0.7. And then the last number is how much we want or less, and so we want 2 or less. And that's our calculations. That's how we're going to throw this in the calculator. So the big thing here, you notice, is identifying what the percentages, the probability is, the trials, how many are you working out of, there's working out of 5, and then how many are you looking for? We're looking 2 or less. And you got to pay attention, is it 2 or less or 2 or more? At most 2 means no bigger than 2, right? So it's only 2 or less, only means 2 or smaller. Okay, so let's type that in and see what you get. Second, distribution, binomial CDF. Type that in. We want number of trials is 5 this time. Probability is 0.7, not -7, 0.7. And 2. Enter a couple of times, and there we go. And again, because we're doing CDF, this probability is actually getting bigger again. We're getting 0.163, which turns into 16.3%. So again, when you're doing CDF, expect bigger answers because you're looking at everything from 2, 1 to 0. And those are most of the options, but there's only 5 students, right? Because the ones that are left are like 3, 4, 5, or the other ones that are left. So that's why it's a good chunk of the options. This isn't any bigger than it is just because they're more likely to graduate than not. So we kind of should be surprised if we only have 0, 1, or 2 people graduate, because there's a 70% success rate, so most of the students should graduate. Okay, let's try one more. This time now, instead of doing at most, we're going to do at least. So we're doing at least. That's the big difference here, at least. Now, at least, when you think about at least, that means that we want 3 or more. 3 or more. Now, the binomial CDF doesn't do or more. We can't do that with or more. So the trick here is when we want to do or more, what we do is we actually take and we use the complement rule. Remember the complement rule? It says you can find the probability of something by finding the opposite and subtracting it from 1. So what's the opposite of 3 or more? Well, the opposite of 3 or more would be 2 or less. Right? Because the opposite of 3 or more, 3, 4, 5 would be options, would be 0, 1, 2, which is 2 or less. And we actually just found that, right? We just found the probability of 2 or less. So we found that one up here. We found that 60%. If you didn't know what this was, you could type in the binomial CDF for 2, like we did here, and find out what this is. But you should find out that it's 1 minus 0.163, and that should give you your answer. So if we take 1 minus, I just took 1 minus my previous answer, I get, so here I take 1 minus this previous answer. I even have the 8 here. So I guess if I don't round it, if I round this 0.8, like my calculator does, I'd end up with 0.83692, or 83.692%. And again, my math lab or my stat lab will tell you what to round to. So you don't have to really be too, each student ought to be careful when you're doing the homework, so you have to round to the appropriate number, but that's what we do there. So if you want to do or more, subtract from 1 the opposite. So again, this is the opposite of 3 or more. So that'd be the idea. If I wanted to find, if I want to find something or more, you turn it into the opposite, so much or less. What's the opposite of this? Subtract that from 1. And that's how you do it. So you got to be careful with that. If they're looking for bigger, then you can't do that because CDF only does this much or less. Okay, last page here, last thing here. So this is about finding the mean, the standard deviation, and the variance if you have a binomial random variable. So we did the mean, standard deviation, variance last section with those probability distributions, and we had the calculation. We learned about the expected value and that kind of stuff. We did find out, thankfully, that the calculator does that when you do one of our stats, as long as you put the frequency list in. This section, because you're not going to have a frequency list, we just have the information, N, P, and X, and Q, figure out Q. You're not going to be able to use one of our stats, so you are going to need to have these formulas. And so these are formulas that you can use to find the mean, the standard deviation, and the variance if you have a binomial probability distribution. So first off, you find the mean by just taking the sample size n and multiplying it times the probability of success. So that should be your average amount of successes, right? Because you take the population, how big the population is, multiply it times the percentage of success, and now you got how many you should expect on average to get, have success. Standard deviation, now you take the number of success, the number of trials times the probability of success times the probability of failure, multiply those all together and square root them, and that is your standard deviation. So that's the formula for standard deviation. Lastly, variance is the same thing as standard deviation, but squared, because variance is always standard deviation squared. So it just doesn't have the square root, right? Because when you square root, it's gone. So most of the time I'll find variance first and then square root it to find standard deviation. So these three formulas, they are not in your calculator. They're not built in. So to do these ones, I do write these on my 3x5 note card for the exam. Make sure you have them somewhere so you can use them. And again, this is just for binomial random variables that have that nice situation where there's success or failure, the only options, and they'll typically give you this information. They'll give you the probability of success, so what's the chance that helps patients, the trial size, so how many patients there are, and that's all you need for this one. They didn't tell us the number of successes because we weren't looking for the probability of successes, we're looking for these mean, standard deviation, variance. So you see that in this case, they actually only give you P and N. Now remember Q, you can always find Q by just taking 1 minus P. So if I take, take 1 minus this 0.7 for 70%, is 0.3 is Q. So Q is 0.3. So now I have all the numbers I need. I know P is 0.7, N is 5, Q is 0.3. Now I can find these things. First off, mean. Mean, this mu for mean is just the sample size, or the trial size, 5, times the p-value, which is the probability, which is 0.7. Multiply those, you get 3.5. So about 3.5 is what we expect. So on average, 3.5 of these people are going to be showing that it's going to help. That's what this, because it's a drug test question. I get legal question, but we see there's a drug test, new drug helps patients. 3.5 patients we should expect to be helped on average. More is surprising, less is a little surprising. It should be around 3.5 most of the time. Okay, and then variance, again, like I said, I'll actually do variance second because it's easier to do that and then find standard deviation. So variance, which is your sigma squared, is going to be n times p times q. So we're going to take n, the number of trials, which is 5, times p, which is 0.7, times q, which is the 0.3, because again, q is the opposite, so 70% and 3%. These two numbers should always add up to give you one whole. 0.7 plus 0.3 is one whole when you're doing this variance calculation. Okay, so if I do 5 times 0.7 times 0.3, I get 1.05. So this is the amount of variance. Again, we're not going to do a lot with variance in this class. We're almost done seeing variance because here we've just talked about how to calculate variance a few times. And that's really what we'll ever do with variance. We're not going to do any more than just calculate a couple times. Later on this semester, we won't really see much of variance. Last thing is standard deviation. And again, standard deviation is just the square root of that, or just the sigma without the square because we're square rooted. So we're just going to take the square root of that 5 times 0.7 times 0.3. So on your calculator, if you already have that answer, you can just hit the second square root and then second ands. So there's a little ans for answer. And what it does is it just takes the previous answer and puts it inside the square root. So you just hit enter. So it's the same thing you'd get if you just type square root of 5 times 0.7 times 0.3. You get the same thing. I just like to use the A and S because it just takes the previous answer that I already figured and throws it in there for me so I can get the same calculation. Okay, so standard deviation for this one is 1.025. I can round it to. Again, my stat lab will tell you what to round to. So, yeah, some questions will have you find the mean, variance, and standard deviation with a binomial random variable. And again, you know you're working with binomial random variable. All they're going to give you is they're going to give you the number of trials and the percentage of success. They didn't give you a chart. You know, when we did probability distribution, we got that chart with all the different values and then the probabilities for each value. And that's when we went and did, you know, the problems the way we did last week. But if they give you just the percentage of success and the number of trials, you can still find mean, variance, and standard deviation, again, using those formulas. So you should be ready for those. So that's it. We are done with 5.2. We're done with chapter 5. So this is the last set of notes for our first exam. So that first exam is the next thing I'll be doing. And then you'll see me next time on the next set of notes for chapter 6. We move on to unit 2.